All right, let's get started. Now, we will be talking about general IV curve of a solar cell. IV would mean current voltage. So when we say IV curve, we're talking about the current voltage curve. Now, one of the first things I need you to know is that maximum power is usually delivered from the PV cell, module or array, if the operating point is the same as that of the knee of the IV curve. Okay, so when we say the knee of the IV curve, this is what we're referring to. See, you can see this is like the knee here. All right, that is the knee of the IV curve. The operating point is actually the point at which the solar module begins to operate. It's the term used to define the point at which the solar module begins to operate. So maximum power is usually delivered if the operating point is the same as that of the knee of the IV curve. That is when you have your maximum power. There is need to deploy maximum power point tracking. Okay, so the maximum power point tracker is usually a device that is expected to respond swiftly when there are changes in the climatic conditions or ambient conditions that impact the PV output. Okay, so it is possible that there is variation in the solar radiation. It is possible that there is variation in temperature. It is possible that there are variations in other, ambient or environmental conditions. And these environmental conditions, especially if they have effect on the output of the PV system, it is good to have maximum power point tracking devices so that when those changes happen, when those variations happen, instead of having an output that is not enough, or instead of having an output that is severely impacted negatively, the maximum power point tracking device would have to adjust in such a way or respond in such a way so that the system and then the operation of the PV system would be adjusted to ensure that the output remains constant. All right, that is why we need the maximum power point tracking device. From what you can see here, you will see that there are two curves in one here. We have the current voltage curve. You can see we have the current on this left-hand axis. You can see we have the current on the left-hand axis, and then we have the voltage as the horizontal axis. Again, we have the power on the right-hand vertical axis, and then you can plot the graph of power against voltage. When you plot the graph of power against voltage, this is what you have. All right, you have this kind of curve, and then when you plot a graph of current against voltage, this is exactly what you have here. Okay, so you should be familiar with these things. All right, let's take it a step further. So like we mentioned earlier, the point on the IV curve where the solar module operates is called the operating point. For a given irradiance and temperature, an operating point on IV curve corresponds to a specific and unique IV value. Okay, so for a given irradiance and temperature, an operating point on the IV curve corresponds to a unique IV value. So for every solar radiation that we have, for every temperature that we have, there will be specific current and voltage that can be measured at all, solar radiations that we have, or time series values, data climatic conditions that we do have. There will always be the current and the voltage for that particular value, for those variations, climatic conditions. So without any external electrical manipulations, the PV module operating point is largely dictated by the electrical load seen by the PV module at its output. What this simply means is that every PV system is connected to a load. Okay, one way or the other, the PV system has a load that they are servicing, has load that they are powering in the real sense of it. So the PV module operating point is usually dictated, affected, or determined by the electrical load seen by the PV module at its output, or that is connected to its output. So to get the maximum power delivered by the PV module, it is therefore imperative to force the module to operate at the operating point corresponding to the maximum power. This is very important. So we have to force the module. The simplest way to make this happen is to force the voltage of the PV module to be at the maximum. So we have the maximum power voltage, and then we have the maximum power current. Okay, so if we can force voltage to operate at the VMPP or regulate the current to the right amount to be at the IMPP, using our converters, this becomes very easy to achieve. Okay, so for every increase in solar radiation or decrease in solar radiation, every increase in temperature or decrease in temperature affects the output of the system. Okay, so if we want to make sure that the output of the system is maximum at all times, we want the, irrespective of the variations that we see, we have to find a way to force the converter, to make the converter force the VMPP or the IMPP is regulated in such a way that, you know, this happens. Because, you know, power is equal to current times voltage. In many cases, power is equal to current times voltage. So if when we notice that variations in solar radiation or temperature is affecting the output, we can either adjust the voltage or adjust the current to ensure that we keep the power output constant. So here's a question you probably want to pay attention to. What if after forcing the PV module to operate at MPP, which means maximum power point, the ambient conditions changes? Okay, so let's say the ambient conditions, the solar radiation drops, and then the power output drops, and then instead of having a drop, a reduced power output, we force VMPP and IMPP to change, to vary, so that we can keep the power high. So if we force them to keep the power output high, because the solar radiation dropped or temperature dropped or increases. So now that we have our high power, what happens if the solar radiation changes back to normal again? What happens if the temperature changes back to normal? That simply means it will affect the output again. So what we usually do is the old MPP will no longer be valid under these conditions. To be continuously at the maximum power point at all times, we would need to keep tracking. Okay, we need to track any such changes in the IV curve and find out the new MPP. And this has to keep happening continuously. The ability to make this happen, or the process of making this happen, is what we refer to as maximum power point tracking. So the abbreviation for that is usually referred to as MPPT. And there are devices that can make that happen. The devices that perform this process are usually referred to as MPP trackers. All right. So most of the PV modules have, you know, MPP trackers, or the inverters have MPP trackers incorporated into them. Okay, so please pay attention to these two. These are important details you want to see. So you can see the variations there. Okay, you could have one maximum power, and then there is a variation in the ambient conditions, and because of that, you force the VMPP or IMPP to a particular value to keep the power constant. And after you do that, another variation occurs. Then you do that, then another variation occurs. So that simply means for every variation that occurs, you know, there has to be something that continuously tracks those changes, and then as it tracks those changes, it has to continuously, you know, adjust the voltage and current to make sure that the power output remains maximum at every change in the ambient conditions. What you see here is the MPPT techniques that we have. It could be direct, it could be indirect. Okay, so we have the fixed voltage method, we have the fractional open circuit voltage method for the indirect method, and then we have the perturb and observe method, and then we have the incremental conduction method for the direct method. Okay, so these are the various MPP, you know, tracking that we have. So what you see here are examples of PV inverters. We are going to talk about those inverters in a couple of minutes. We're going to look at the types of inverters and then how they work. Inverters can be classified based on their size. They can be classified based on their mode of operation or implementation topology. What inverters do basically is to convert DC electrical energy to AC electrical energy. The solar energy coming to the module is converted to electrical energy, and that electrical energy is always DC electrical energy. So if we are going to power AC load, the DC electrical energy has to be converted to AC electrical energy before we can supply them to power the load that are AC in nature. The DC is usually a single line. You can see this single line here representing the DC, and then the AC is usually a wave-like, it's a waveform. Okay, you can see that wave here. Okay, so what the inverter does is to convert this DC energy, this DC, to an AC energy output. Let's quickly look at the type of inverters we have and try to explain their topologies, their implementation topologies, how they operate, and so on and so forth. We have the central inverter, we have the module inverter, we have the string inverter, and then we have the multi-string inverter. So the central inverter, in terms of size, it usually ranges between 3 kilowatt and 100 megawatt. The module inverter ranges between 50 watt and 500 watt. And then the string inverter ranges between 500 watt and 25 kilowatt. And then the multi-string inverter ranges between 1 kilowatt and 10 kilowatt. When we say a central inverter, what it simply means is that what we have here, you can see these are modules, okay? These are modules, okay? These are modules, okay? So we can refer to these as our entire module array. So what you will notice here is that all the modules are connected. We have the PV farm or the PV power plant, and then there is going to be just one single inverter called the central inverter connected to the PV array, okay? So just one single inverter will be connected to the PV array. So that is the topology that we have here. And you will notice that it actually has like the highest size. So it ranges from 3 kilowatt to 100 megawatt. Then we have the module inverter. What happens here is that each of the module has its own inverter, all right? So you can see this is an inverter connected to one module. This is another inverter connected to one module, and this is another inverter connected to one module. So depending on the number of modules you have, each of them will have their own inverter. And you usually, this kind of inverter usually could be in the range of 50 watts to 500 watts in terms of size or capacity. Then we have what we refer to as the string inverter. How does a string inverter work? Sometimes when we have, or most times when we have a PV farm or a PV array, all right, PV array, let's say we have 20 modules or 50 modules or 100 modules or even 1,000 modules or even 3,000 or 5,000 modules forming a PV farm. It is possible to string some modules together, all right? So we could connect 80 modules. For example, on one of the PVs that I have worked on, we have witnessed a situation where we had to string 80 modules together. So the 80 modules string together will have one inverter. So that means if we have 1,600 modules, it simply means we are going to have 1,600 divided by 80 inverters, all right? So 1,600 divided by 80 would mean 20. That simply means that particular PV farm would have 20 inverters if we have 1,600 modules installed there. And each string is made up of 80 modules connected to one inverter. Okay, so that would mean that with 20 inverters, each inverter connected to a string of 80 modules, we would have our PV farm properly connected to all, to the available inverters that we have. All right, so it's a situation whereby the modules are connected in a string, and then the string is connected to just one inverter. So you can call this one string 1, and then you have another one, you have string 2. If we have 1,600 modules, it means we are going to have 20 strings. Okay, 20 strings would mean 20 inverters, and each string would have about 80 modules along the line. All right, that's that about the string inverters. And the size is usually from 500 watt to 25 kilowatt. Then again, we have what we refer to as a multi-string inverter. Okay, this is another interesting, type of inverter that we have. And one of the major disadvantages of some of these inverters, as good as they are and as powerful as they could be, is that some of these topologies are usually very expensive. What happens in the multi-string inverter is that you first of all have a DC to DC inverter connected to one string, as you can see here. So each of the string, let's say we have 20 strings, each of the strings will be connected to DC inverters. Okay, so all the DC inverters will then be connected to one DC to AC inverter. The advantages and the disadvantages of these I'm going to explain to you in a couple of minutes as we go ahead. All right, and the sizes that we have for this kind of connection is usually between 1 kilowatt and 10 kilowatt. Now, as we speak, there are some changes to some of these capacities and sizes. Things are changing every day. Okay, so on a daily basis, we have to update ourselves to make sure that we have access to the latest data, depending on what we are working on at the time. I've been able to briefly give you an overview, a simple overview of what all the 4 types of topologies of inverters we have, what they look like. Now we're going to quickly look at their advantages and disadvantages very briefly, so that you can connect that to the discussions we just had. For the central inverter, one of the advantages is that it increases the ease of system design and implementation. Okay, since we are going to have just one single inverter, a large inverter that is going to be somewhere, it's going to reduce the amount of complications or complex designs that we are going to have when we are designing our PV system. Okay, that's one major advantage it has. Also, Three-phase connection allows balanced power supply. It has the least cost per kilowatt. This is one major turn-on for a lot of installers because everybody is looking for how they can get the maximum output by spending less on installation cost and other associated costs. So it is not as expensive as other inverters. It has the lowest cost possible when we talk about topologies of inverters, and it also has very high efficiency. If the efficiency is high and the cost is low, what else do we need? And of course, it also reduces the complexities of design. So what else do we need? These are advantages for using the central inverter. But then, despite the fact that all these advantages are good and they're okay, one of the drawbacks is that, one of the disadvantages it has is that you will need to use a lot of DC cables, because in some cases, the central inverter will be located in places that are not too near or close to where the PV farm is. So that means that the DC energy that is supplied by your PV system, you have to transport it to where the inverter is before they can be converted to AC. So you will make use of long DC cables, and then higher DC cabling costs will be incurred, because the longer the DC cables, the more cost you would have to incur, for making those DC cables available, all right? DC faults are actually difficult to interrupt. That's another major challenge, okay? So you might want to think twice and ask yourself, okay, if you weigh the advantages and disadvantages, which one, will offset the other? Which one works better for you before you can make your final choice? All right. Also, another disadvantage it has is that it has just one maximum power point tracking channel. Just one maximum power point tracking channel. So if there is a module mismatch, or if there are issues along the line that are connected to the maximum power point tracking, performance will continue to decrease. Okay, so that simply means that you cannot segregate, you cannot dissociate, some modules from other modules. All of the modules are passing through just one single inverter that has just one maximum power point tracking channel. So if there is an issue with that tracking channel, minor or major, it's going to continue to decrease the output of the system, or eventually shut the entire power system down. So these are the advantages and disadvantages of using central inverter for your installations. Okay, let's take it a step further. So here what you will see is a typical example of what a central inverter looks like. You can see it's just going to be located in one single point, and then you can see the parts of the inverter. Okay, so you can see we have the heat exchanger, the stack fan, the inverter bridge, the AC grid contactor, we have the AC circuit breaker, and all of those. Okay, but you might just want to go through this and be familiar with, the terms used to label the components. All right. Now we have a second type of inverter that we want to talk about, which is called the string inverters. Like I told you, the string inverters, they are kind of inverters that are connected to several modules that are stringed together. Okay, so each string will then have one inverter before we have our final output. So the advantage of this is that it has multiple maximum power point tracking channels. That simply means that if there is a problem with, let's say this is a string connected to this inverter. Okay. So, and let's say we have 10 strings. This is string 1, this is string 2, and then we have 8 more strings to make it 10 strings. It is possible that there will be a problem with the maximum power point tracking located in this string with this inverter. All right. The only thing that would happen is it is only the output coming from this inverter that will be affected. The other 9 inverters will be functioning perfectly well, and only the output from this inverter will be affected. So that simply means you can actually isolate this entire string from the total output such that it will not affect the output of the other inverters. This can actually happen, right? But in the case of central inverters, it is difficult to isolate some modules. It is difficult to isolate the maximum power point tracking channel because we have only one. And once you isolate that, you're isolating the entire power system. But in this particular case, you can isolate an entire string. Again, it is more resilient to mismatch than the central inverter. So a string inverter is more resilient to mismatch than central inverter. It can withstand mismatch much more than central inverter can withstand mismatch. Each string is independently operated at its maximum power point, thus guaranteeing a higher energy yield. We've talked about this. This is the third advantage of using a string inverter. Then it is smaller than the central inverters. It is not as big. It is not as big as the central inverters. Okay, so this makes it easier to be moved. Then some of the disadvantages is that the implementation is more complex since we have more MPP tracking channels, and then we have strings that we have to connect many modules to. It simply means that there will be some design complexities in the implementation of this particular topology, and then the cost is higher than the central inverter's cost. You might want to look at the cost. If the disadvantages for you outweigh the advantages, then you might want to consider another option. But if the advantages outweigh the effect of the disadvantages, then probably this might just be a good option, a good topology for you, depending on what you want to use your PV power system for, depending on where you want to install your PV power systems, and a couple of other factors that are involved. All right, let's take it a step further. We have what we refer to as the module inverter, or you could call those micro inverters. Those are the inverters, those are the topologies where we have each module connected to its own inverter. Okay, so the inverters are way smaller, all right, and each module will have their own inverter. An advantage of this kind of topology is that each module has a dedicated inverter with an MPP tracker. So it simply means that one module has its own MPP tracking channel. It is also resilient to partial shading effects. This is resilient to partial shading effects. So it simply means that normally when you have 20 modules stringed together and then one of the modules is experiencing partial shading, it will affect the output of the entire modules connected to that string, connected to that inverter in the string. So if there are 20 modules connected to one string and we have just one inverter, the output of the entire module or this inverter will be dependent on the lowest, lowest output in the entire string. And it is the one that is shaded that will give us the lowest output. So that means what we will get as the final output will be the lowest output of all the systems that we have, if we have 20 strings connected together. But since we have just one string here, if only this module is shaded, only this module will be affected. All right, so that is why it has to be resilient to partial shading effects. It provides the highest system flexibility because each module has its own tracking device. Each module has its own inverter. Each module has its own maximum power point tracking. So it's going to be very flexible, okay? And then extending the size of the system is simpler in this particular case. So you can increase the size of your system. One of the key advantages of PV systems is that they are modular. Being modular simply means that you can easily and quickly add more capacities to already existing capacity, as long as you have space and you have the money. So if you have plans to install, let's say, a 1,000 kilowatt peak PV system, and at the moment, all you have can only afford 200 kilowatts, okay? So you can install the 200 kilowatt, and then every month you can keep adding 100 kilowatts every month. And then it might take you 1 year or 2 years to eventually complete your 1,000 kilowatt. And easily, if you are using a micro inverter, topology, easily you can add all of these, additional modules to the already existing modules that we have. DC wiring costs are greatly reduced. The cost of DC wiring, it's greatly reduced because, I mean, the inverter is already connected to the module. So you only need just a short cable to connect the module to the inverter, very short cable, and then you have your DC energy converted to your AC energy. Then it comes with its own disadvantages too, high investment and maintenance cost. So it simply means that if you are going to have inverters on all the modules, then you should be ready to spend money. So the investment cost is high, okay? The maintenance cost would also be high. Then high cost per kilowatt than central inverters and string inverters. So it is more expensive than central inverters and string inverters, all right? Because cost per kilowatt, is way high. All right, let's take it a step further. So if you look at what we have here, this gives you an idea of a micro inverter. You can see that we have a module. This is module 1, module 2, 3, 4, 5, 6, 7, 8. So these are 8 modules together here. And then as you can see here, you will find out that we have each module connected to its own, connected to its inverter. As you can see here, we have about 1, 2, 3, 4, 5, 6, 7 inverters. And then you will see that each module has its own inverter. The same thing goes with what we have here. We have about 6 we have about 6 modules here, and each module has its own, inverter, right? So you can see the connection, huge connection here. And then the rest of the circuit can also be seen here. So we have another type of inverter called the multi-string inverter. Okay, so like I mentioned earlier, the multi-string inverter, you have, first of all, your DC to DC inverters connected to strings, and then you have just one single inverter going to the grid. So all the DC to DC inverters will actually be connected to one single AC, grid connected inverter. And then now, what are the advantages of this kind of topology? Each of the strings is power processed using the low power DC to DC converters. I just talked about this. That's a major advantage of that. Okay, so that simply means that all the energy coming from the module, you process it already with the DC to DCs, you refine it with a DC to DC converter. Each string has its own MPP tracker implemented alongside the DC to DC converter. You know what this means already. Then the disadvantages of the multi-string inverter is that the investment cost is also high, very high. And then the cost per kilowatt is also very high compared to the string inverters, the central inverters, and then other types of inverters that we have. So I think this is expensive. What you want to ask yourself is, when you look at the economic aspect of it, and then you look at the technical aspect of it, you want to weigh both sides and ask yourself, which one offsets the other, which one works better for you, which one can you afford, and then which one gives you, a better output or outlook when you compare both technical and economic analysis together, or the techno-economic analysis, when you compare that, which one gives you a better outlook. Okay, PV inverters, whatever they are, whatever the topology you use, they have some characteristics. Okay, so one of the characteristics is that they have increased efficiency. Okay, you would also notice that they have maximum power point tracking channels. Okay, each of these PV inverters have maximum power point tracking channels. This simply means that for all the variations we have in the ambient conditions, all right, this inverter would ensure that we have maximum power delivered to our load at the end of the day, all right? Okay, they also support anti-islanding. Islanding is an unsafe condition for workers, is an unsafe condition for the entire system, okay? It's a condition in which a distributed generator continues to power a location when electric grid power is no longer present, okay? So when electric grid power is no longer present, you find out that the DC generator continues to power a particular location, and this is dangerous because those workers, once there is no electric grid, they will assume that there is no power. So if care is not taken, the DC generator will continue to power the grid, will power the location, and then those workers might be at danger. It's very unsafe for workers and the entire environment. Okay, so PV inverters have anti-islanding effect. That simply means they make sure that doesn't happen. You make sure that we don't experience islanding at all. Okay, so this is a huge advantage for PV inverters. And then you see that they are protected from H2 and temperature, and then they have low harmonics. Okay, by harmonics, for some of us who are either electrical engineers or familiar with terms like this would know what it means. Harmonics are actually unwanted higher frequencies that create distorted wave pattern. Okay. So unwanted high frequencies, okay, and they usually create distorted wave patterns. We don't want unwanted, higher frequencies, unnecessary higher frequencies, because it will lead to mismatch between the grid voltage and the voltage of in the output voltage of the system. Okay, so the voltage have to be synchronous. They have to match. What this does is that when we say it has low harmonics, it simply means it reduces that effect of providing higher frequencies that we don't want. So it has an increased lifespan too, all right? So these are characteristics of a PV inverter. You might want to know them. These are important. It's important to be familiar with all of these characteristics. You really want to know them.